here? Can you all kind of see it in the background? I'm covering that up, all right? And all I'm doing is asking you to look at what's happening at 2, right? That's what that question is saying. What's happening to this function at 2? And the answer is 8. So at 2, you have a point up here, and there it is, right? That is college algebra. That's what college algebra is about. I hand you a function. I tell you to plug in a point. You plug in the point. You get the output. You're done. That's college algebra. Nothing crazy here, right? Calculus is not this. What calculus is going to do is this. It's going to say, instead of looking at that, I actually don't care about what's happening at 2 anymore. So ignore what's happening at 2, completely ignore it, and tell me what's happening near 2. Near 2. Next to 2. Close to 2. So what do I mean by that? Here's 2, right? Here's 2. And I'm asking you to think about what happens, what is the function doing? What is the behavior of the function as my values of x get close to 2? Close to 2. Close to. What do I mean by close? We have our first ambiguous word. Close. Are we close? Is this close? Do you feel close? Am I close to SeaWorld? You all know where SeaWorld is? Yeah. Am I close to SeaWorld? Some people are saying yes. Am I close to the sun? No. Okay. Okay, so SeaWorld is very close to me compared to the sun, yes? Yes. But what about like Alpha Centauri, which is the next nearest star other than our sun? The sun is pretty damn close compared to Alpha Centauri, right? So close is a relative word. It depends, right? It is really relative. And so I'm going to use this word, close. And in this class, we're going to have to wave our hands at that idea a little bit. We're just going to have to agree that close is ambiguous and kind of, I don't know how to explain this in a way other than we could get very rigorous with this idea of close, but then this calculus class becomes a lot more difficult. We have to use pure mathematics to do it, and it's, for me, a direction I don't like to go in this class. So what I'm going to do is ask you, somebody in here, to give me a number that's close to 2, but from this left-hand side. 1.9? Okay. Do you all agree that that's close? Sound good? 1.9. So if I plug 1.9 in here, I would have to plug it into the function, right? And it's going to spit out a number. I'm not going to do it on my calculator. I'm just going to look at the graph. Do you all see that at 1.9 I'm up here? Not quite up there at 8, right? 8 was what was happening at 2. But at 1.9, I'm up here. I'm not quite 8, but I'm up there in the 7s, right? 7 point something. Yeah? But is 1.9 really that close? What's the number closer? 1.99, right? So what if I do 1.99 in here? If I were to plug that into this, guess what would happen? I would get another number, but it would be even closer to 8. Do you see that it's kind of rising up towards that point? But again, we're not allowed to look in here. We're going to ignore that that's even there. But from the left, do you all see my graph is going up towards 8? Yeah? What's happening if we come into that value of 2 from this side instead? What's a number that's close to 2 but from this side? 2.1, right? So I could do 2.1. And there, I'm up here, right? Like that. I'm actually above 8 there, aren't I? And then I could get even closer. What would be a number closer to 2 from the right side? 2.01, right? Could I get closer? 2.001, closer? 2.001, right? So I'm going to, instead of doing this by writing it down, I'm going to have the computer do it for us, all right? So watch what happens. I'm going to approach from the left-hand side. And what you'll see here is what's in blue is the x-coordinate, and the purple is the output, is the y value. And I want you to pay attention to this as this gets closer to 2 from this side. So it's almost like we're walking, like we're a person walking along this graph, and we're trying to figure out our height off the ground, okay? So as I move into 2 from the left, moving along that point, 4 point something, 6, there we go. Let me, see the y value? What are we at? 7.9598, pretty close, yes? To 8, we're getting closer and closer to 8. Look at that, 1.999, I'm at 7.996. Doesn't it look like the closer I get to 2 from the left, the closer the function gets to 8? What, do I actually ever get to 8? Only if I get to 2, right? But if I stay a little bit to the left of 2, I'm always going to just be close to 8, but not quite there, right? Same thing happens from the other direction. If I come in from the right-hand side, where am I? Oh, wrong thing, sorry. This one. Here I come. There I go. So I'm walking along, right? You see me? Walking along the graph from the right-hand side. I'm going to go up past 8 first, aren't I? I'm going to go up past 8. See, but right here, I'm not very close to 2, am I? I'm at 2.732. So I'm going to come in here, get as close to 2 as possible without going over. Let me get this one out of here. And see what's happening to this value right here? See how that's getting closer to 8? I'm almost to as far as I have this program to go. There we go. That's as far as I have the computer program to go. So 2.001, that's pretty close to 2 from the right, yes? And look at my value, pretty close to 8, right? But a little bigger than 8. So from the left, we were approaching 8, but we were always a little below 8. From the right, we were approaching 8, but we were always above 8. But from both sides, it's going to 8. Do y'all see that? Okay. Let's look at another one. So I'll reiterate one more time before we actually do it. College algebra. What's happening at 2? 8, right? That's college algebra. Calculus. I don't care what's happening at 2. I want to know what's happening as we get close to 2. Close meaning 1.999 or 1.99999 or 1.99999. How about 1? Oh, hey, hold on. This is kind of an interesting idea. What about this number? 1.999 forever. Is that the number that's right next to 2? Anyone have an idea here? All right, think about the number line. Here's 2, right? We said 1.9, 1.99, 1.999. We could keep getting closer and closer. Is that the number right next to 2? Any guesses? What do y'all think? I heard yes. Anyone think it's not? The number right next to 2? It looks like a pretty damn good candidate for the number right next to 2, doesn't it? It's not. I'm going to show you. You ready? I'm going to show you why this is not the number right next to 2. See if you can follow this. It's not super crazy, but just see if you can follow the logic here. I'm going to call this number x, okay? I don't know what it is other than 1.999 forever. All right? Now what I'm going to do is I'm going to multiply it by 10. Now I'm doing this because what happens if I multiply a decimal by 10? What happens to the decimal point? It goes to the right one. So that's 19.9, how many 9s? Right, this just moved over, so how many 9s do I have? Infinitely many still, right? So I can go 9 and just put a bar over it again? Yeah? Okay, why did I do that? Well, I did that so I can do the next step. I would like to know what 10x take away x would be. So just algebraically tell me right now, what's 10 x's take away 1x? How many x's would you have? 9? Okay, but what was 10x? According to us, it was 19 0.99 forever, right? And then what was x? 1.999 forever. And if I subtract those, what would happen if I subtract these? What happens to all the 0.999s? They cancel out, right? So those are all gone. And you just have 19 minus 1. What's 19 minus 1? 18. So that means that 9x has to be 18. Divide both sides by 9, and what do you get? X is what?
2.
X is 2. But x was 1.999 forever, which means that this number actually is 2. Yeah. So I know it's crazy, right? The number 1.999 forever is the number 2. It's not the number right next to 2. It is 2. So there is no number right next to 2. It's impossible to find a number right next to 2. Like if you give me a number line, take the number 2, and go try and find a number right next to 2. If you claim you have it, like let's say you think you found it, right? I can always find another one. Because all I have to do is take your number, whatever it is, right? Whatever that number is, I take your number and I take 2 and I take their average. The average of two numbers is always the number right in the middle of them. So as soon as someone claims they found the number right next to 2, I can come up with another one that's even closer. And I can just keep doing that forever. So there is no number right next to 2. There's not. There's infinitely many. It's a really strange part of our number system, which is why, I'm going off on a little tangent here, but I think it's worth it. That's why when you're doing interval notation, and you're saying something like, hey, I want all the points between 1 and 2, but I don't want to include 1, I don't want to include 2, right? To write that in interval notation, you write this, right? And we use parentheses, not brackets, right? That's what we do. Do you all agree that if there was a number right next to 2, like let's say 1.999 was the number right next to 2, then we wouldn't need this notation anymore, would we? We would just say 1.99 forever bracket, because that would be the number right next to 2. But see, we don't do that because there is no number right next to 2. So we have to just say the 2 with the parenthesis. That means all the numbers leading up to 2 without actually getting to 2. All right, sorry, I went off on a little tangent there. Apologize. Next example. I need to make this a little bit bigger. That might be too big. All right, I want y'all to look at this picture right here. This is a graph of a function. I've hidden everything from you except what's happening at 2, right? Can y'all tell me what the value of this function at 2 is? What is the value of this function at 2? Just by looking at that picture. It looks like 8 again. Do y'all see that? Now this is an open circle. Open circle means it's not part of the graph, right? So this is open circle, but that's a solid circle. So that's happening up here at 8, right? So this is college algebra. I'm saying ignore everything else. What's happening at 2, that's it, right? College algebra. Now the calculus. Does this graph do the same thing? You don't know yet, right? I haven't shown it to you. But is it going to come into 8 from both sides? I don't know. It depends on the function. So let me reveal the function to you. Maybe. All right, so look at that. What happens if you're moving along this function from the left, moving this way, approaching 2? So you're walking along here. What's happening to your y value? Where is it approaching? It's getting closer to 8 again, right? We're headed up towards 8. Now I'm going to hide the middle because I don't want you looking at the middle because we're doing a calculus question now, right? You're not allowed to look at that anymore. So as we come in from the left, our y value is approaching 8, right? As we come in from the right, what happens? We go up and then we come back down. What does it look like it's approaching this way? 4, right? They're not the same. In the previous problem, at 2 we were at 8, right? At 2 we were at 8. From the left we went to 8. From the right we went to 8. In this picture, at 2 we were at 8. But from the left we're headed to 8. The right we're headed to 4, right? Just to show you that it doesn't always have to match, right? This is an example where it's different from each side. Look at this one. This is a different example. What is the value of this function at 2? 6, right? It's 6. That's the algebra. Now let's do the calculus. Let's cover that up. Let's talk about left and right. From the left, where's this function headed? Up to 8. And from the right, it's headed to 4. Those are 3 different values, right? At 2, it's 6. From the left, it's 8. From the right, it's 4. Does anyone have a question or confusion or anything on this so far? I don't know why. I'm kind of giving these things away here. Oh, hard to see that. That's an open circle. It's hard to see it, but that's an open circle. Right, so if this is an open circle like this, what's the value of the function at 2? It's undefined, okay, because there's no point here, all right? So this would be undefined. And now let me reveal to you what's happening near it. So from the left, if we're coming along here, we're headed to some value. Now, it's hard to see what this value is. I'm going to have to tell you what it is. It's actually -1/4, okay? That's what it's heading to. The main thing I want you to see here is that from the left, it's headed somewhere, isn't it? And from the right, it looks like it's headed towards the same place. And if I take that thing out of the middle, you can see that what we have there in that graph is a hole. Right, there's a hole in that graph. It's not a very good. All right. So at 2, it's undefined. From the left, we're headed to the same place we're headed from the right. Okay, I've changed our x value. We're no longer looking at 2 anymore, because that 2 was just arbitrary. I just made it up. We could be approaching anything. So look at this right here. At 0, -1, 1, at 0, what is the value of this function? Undefined again, right? I'm going to put UND for undefined. So do you all agree at 0 we're undefined? All right, now let's look at what's happening from the left and from the right. From the left, where are we headed? 1, right? We're headed towards 1. And from the right, where are we headed? 1 as well, right? Okay, I want to know what's happening at 0. And you know what? Let me show you the function this time so you can actually see this function. This is the function's f of x equals sine of 1 over x. So I'm interested in what's happening at 0. So what's f of 0? It's sine of 1 over 0, right? But 1 divided by 0 is undefined, right? This is undefined. All right, now you can't tell from my picture that that's undefined, right? This looks like a complete mess in here, doesn't it? What's happening as I come in from the left? Let's go to Desmos. I'm going to have Desmos graph this. Maybe Desmos will do a better job. See how Desmos handles this. Okay, that's Desmos's graph. Let me zoom in. Let me try and change the scale here. Whoa. Come on, Desmos. What the, right? This is a crazy graph. Something really weird is happening here. So think about, this is a hard function to understand. Sine has a period from 0 to 2 pi, right? So if you graph the sine function, not that one, but if you graph sine of x, it looks like this. And then it continues and it repeats itself, and it does that forever in both directions, right? It does that. That's what sine looks like. Well, what's happening here is that as you try and we're trying to wear 0 in here. Here's 0. As we try and move along this function and we try and get closer to 0, what happens to this number? So this is an extremely important idea right here. If I take the number 1 and I divide that by, let's say we're moving in here. You know what? Let's come in from this side. Okay? Let's say we're at 1. What would happen if I plug in 1 right here? We just get 1 over 1, right? Sine of 1, that would be, we'd have some answer. Let's move into 1/2. What happens when I plug in 1/2 into this? What's 1 divided by 1/2? 2, right? So now we're at 2. Is sine of 2 defined? We can plug 2 into sine. 2 is just the angle, right? So 2 radians. What happens when I plug in 1/3? What comes out of this? 3. Does sine of 3 exist? Yes. What happens when I plug in 1/4? 4, 1/5, 5, 1/6. How many fractions are there in there? Infinitely many. So what's happening is that as you try and approach 0 from the right, it's trying to draw the sine function, but it's trying to draw infinitely many periods of sine in this small compressed area. And so it loses its mind kind of here, right? It loses its ability. Here's a better example, is that we come in from the right, it's trying to draw the sines, but because as we move in on the fractions, we get like 1, then 2, then 3, then 4, then 5, then 6, it's trying to draw the sine periods, more and more of them as you get closer and closer to 0. So it's like infinite oscillations. And so would you say that we're approaching anything? Like from both sides, right? We already know at 0 it's undefined, because can't divide by 0. But from the left, we have these oscillations, right? So we're not approaching the number, are we? We're just like going back and forth. And same from the right, we're just going back and forth. So not only is it undefined at 0, it's not headed towards anything from the left or the right. This is a very strange function. Yeah? Would you agree? That's just to show you things can get crazy, right? That's all that example's for. Let me get to my notes. A few more of these. I don't like that problem. Let me do it. I'm going to do this one on Desmos because look at that graph right there. That's the graph of 1 over x. I'm interested in what's happening at 0. So what's f of 0 here? Undefined. Right? You can't plug 0 into this function. 1 over x. What's happening as we approach 0, I feel like I'm going to sneeze, hold on. Okay. As we approach 0 from the left, so imagine you're walking along this graph, we're approaching 0, trying to get close to 0, what's happening to you? You're headed down forever, aren't you? And that down there is called negative infinity. So as we come in from the left, we drop down to negative infinity. How about as we come in from the right? We go up to positive infinity, right? So what we're starting to realize is that you can talk about a function at a point, but you can also talk about what the function's doing as you approach that point from two different sides, right? And different things can happen. You could be headed somewhere. You could be headed to infinity, negative infinity. You could be oscillating. There's all these different scenarios. This is our last one. Look at that one. 1 over x squared. What's f of 0? Undefined still, right? Can't plug 0 in. What happens when we approach from the right? Goes to infinity. It's coming from the left. Positive infinity as well, right? All right, so this idea of coming in from each side, right? This idea has a name. It's called the limit of a function. So this is the general idea of this thing called the limit of a function at x equals a. So basically, when we find the limit of a function at a point, we are inspecting the behavior of the function near that point. So we start off by the first example. I said, hey, let's look at what's happening at 2, right? Then what's happening is we get close to 2. In this definition, the 2 is the a. So we're saying, hey, find the limit of a function at the point x equals 2 means we're inspecting the behavior of the function near that value of 2. We do not care about the actual value of the function at 2. We don't care. We inspect the behavior of the function. When we do that, we can approach it from the left or from the right, right? We can come in from both directions. When we're approaching from one side, one of the following can occur, right? So when we are coming in from one side, we could have, let me zoom this back out because it looks all weird like this. Still looks weird. Just tell me if it's too small. Is that okay still, everyone? So when my students last semester, they didn't like this because it's a little intimidating, sorry. When we approach a function from one side, one of the following can occur. First, the function can just approach some number, right? It can be headed to some number. Or it could oscillate infinitely many times, like that crazy one we saw. Or the function can approach positive or negative infinity. It could go up forever or down forever. Those are the only three things that can happen, all right? That's it. It's either headed to a number, it's going to oscillate and go crazy, or it's going to go up forever or down forever. That's it. Remember, I can't say this enough. We do not care what's happening at 2. The limit is what makes this a calculus topic. So now, with that, we define what's called the left-hand limit and the right-hand limit. So we already said we can approach from either side, right? So when we come in from the left, we call that the left-hand limit. We come in from the right, we call it the right-hand limit. Left hand, right hand. And because we want to ask this question so frequently in this class, we have special notation for this. So you know how up to this point I've just been saying to you, like, hey, what's happening as we come in from the left? What's happening? Instead of me saying that, I need a mathematical way of saying it. So here's the notation. It's going to look a little ugly, but you'll get used to it. So anytime we are looking at some function, and I want to come in from the left, here's what I'm going to write. A left-hand limit, here's what I'm going to write. Lim, which stands for limit, x with an arrow to the number I'm approaching. I'm going to give you an example next to this. Limit x approaches 2. You can either put this below the lim or down off, down to the right. It's up to you. I'll do this exclusively in this class. I'll just drop it right below the limit. And then, do you see this little negative sign right here? That little negative sign is not a negative in front of the 2. It's up on the top right-hand side. That's what tells you it's a left-hand limit. Because the negative is saying, hey, think about the number line. The negatives are over here, the positives are over here, right? So we're going to come in from the left. We're going to put a little negative sign there so you know that I'm coming in from the left. And then whatever the function is. I'm going to put a function here. This right here is a specific example, all right? This is a specific example for you to see right now of a function that I'm asking you to find the left-hand limit of. So approach 2 from the left of this expression. Now, how would that notation change if I want to come in from the right? What do you think is going to change? That little minus is going to become a positive. See that? That would be a right-hand limit. So I come in, all right, limit x approaches 2 from the right of x squared minus 4 over x minus 2. This is a right-hand limit. Right-hand limit. This is a left-hand limit. See, the only difference between these two notations is that minus and that plus. That's it. But that lim is our new calculus notation. Yes?
Well, we need to know oscillation, like the discontinuities.
That'll come. That'll come. We're not ready to talk about discontinuities yet, but we will get to that. All right. So that's just notation, right? That's all that is notation. When it comes to calculus, right, there's calculus 1, 2, 3, and then there's more than that. There's other topics subjects that include calculus. The limit is the heart of all of calculus. This concept of getting close to something without actually being there is where everything is born from, right? Now, we have a third notation. Look at this one right here. Do you see that one? What's the difference on that one?
On both sides.
Yeah, there's no plus or minus, right? Do you see I didn't put a minus up there and I didn't put a plus? If you don't see a minus or a plus in the top right-hand corner, then that is not the left-hand limit or right-hand limit. That is called the limit. And what it means is that you have to check both sides. All right? So the third one looks like this. Limit x approaches 2, x squared minus 4 over x minus 2. That is just called the limit. So if you think about it, this means you only have to check from one side, right? This means you have to check from the other side, from the left and from the right. This means you have to check from both sides. So for this, you can ignore the right-hand side, which means you could get an answer, right? And it doesn't matter what's happening on the other side. You could still get an answer for just this. This one, you could get an answer. It could be different than that. Let me just draw a picture. Look at this one right here. You know what? I'll bring one up. We're gonna just bring an example up.